So here in lecture 9.4, we're going to continue looking at iterative improvement placement. In the previous lecture, we showed a very simple scheme for doing a placer. Randomly locate the gates on the grid that we use to model the chip, randomly perturb or swap the gates, measure the estimated change in the wire length, and just continue this until things stop getting better. And what we showed is you can actually take a pretty bad placement and make it an okay placement. The problem is you can't make it a very good placement. And it turns out that what one needs to be able to do is not only to perturb randomly the placement to make it better, but in some interesting and controlled manner, we need to be able to perturb the placement to make it a little worse. There are interesting problems with local minima versus global minima, and we're going to talk about all of that in a lecture that's called hill climbing. This is the sort of the generic term for the kind of technology that we need to build a better quality placer. So let's go look at iterative improvement with hill climbing.
What's the problem with that simple, random, iterative improvement placement algorithm that I showed you in the last lecture? It looked like it was making good progress. You know, we started with a wire length of something like 45,000, and we fell to a wire length of something like 25,000 for that little 2,500 gate problem. That sounds like a pretty good answer. It's okay, but it's not as good as you can do, and it turns out to be really surprisingly far from how good you can do. And in order to give you some sense of why that happens, I need to sort of perform, if you will, sort of a thought experiment. Imagine that you could plot the total sum of the half-perimeter wire length for all possible placements, and you could make a graph, right? And so if you would, the x and y axes of this graph would be all possible placement solutions you can find. Now look, you cannot do this, because if you have a layout, as I just showed you, with 2,500 gates, this is a 2,501 dimensional graph. The first 2,500 dimensions are every place you could put every gate, and the 2,501st dimension would be the wire length. So just pretend that I could graph this thing. All right, and so I'm showing you two dimensions on this little plot, which has a whole bunch of hills and valleys. Got a great big peak in the middle, and then a medium-sized peak, and then some big deep valleys on the left and the right. Imagine that you could plot this. So the vertical axis is the sum of half-perimeter wire length, and I'm looking for small. What is true about the random iterative improvement method that I showed you? What is true is that I only took swaps of the gates that improved the wire length. And so, said differently, the first thing I did was I generated a random initial placement. That puts a point someplace on this landscape of hills and valleys in the cost. And I'm just going to show that initial random placement as this orange circle. These things are called, by the way, balls and hills diagrams. No surprise. Right, so the hills are all the possible cost values for all of my solutions. The ball is the first random placement. And you know what? That ball is probably pretty high up on a peak someplace, because you know that random placement, that's probably really bad. It's probably got a really big half-perimeter wire length. And the problem is that every time I took a swap, I accepted a swap, I only accepted swaps of the gates that made the wire length better. So I only went downhill on this conceptual hills and valleys cost landscape. And you know what I did? I fell in some local minimum. I fell in a local minimum kind of close to the random initial placement I started with, which was probably pretty bad. And so here's the problem. These kinds of random iterative improvement techniques that only take changes to the layout that make the layout better, which is to say have less half-perimeter wire length, they easily get stuck in local minima. And the problem is that there are lots of better answers. There are lots of less bad local minima and better, more higher quality, smaller wire length global minima, but I don't know how to find them. I need some other ideas. So what I'd really like is a method that, instead of only going downhill from the random initial placement and sort of, falling into the nearest local minimum, I would like a method that could go uphill and maybe get to better placements. And so I'm just going to show you the little sort of example. An uphill method would allow me to go for a time exploring placements that are worse than the last one, in the hopes that I'll go up over this peak and I'll start falling into a better global valley. That would be really wonderful. But wow, that seems incredibly hard. And I'm going to circle the big problem here. How would I control this? The reason I showed you the simple random iterative improvement placement is easy to explain. There's a grid. There's one gate per slot in the grid. I measure the sum of the half perimeter wire lengths. I randomly grab two gates. I swap them. I see if things got better. I keep it if it got better. And I go until I'm tired. That sounds very simple, but it works. How would I control a placement method, a placement algorithm, if I'm allowed to grab two gates, exchange their positions, and make the placement worse? How will it ever converge? Well, it turns out there's an answer. So let's sort of draw a diagram to just sort of summarize where we are. The kind of placer that you know right now is random iterative improvement, but these things actually have a name. This is a greedy algorithm. A greedy algorithm is one in which every decision you make is a positive one. You always just sort of do the next best thing you can do. So, step one, you grab two random gates, 1 and 2, and I'm just showing you a little tiny version of that grid that had 1, 2, 3, 4 gates in it, 2 black gates, 2 red gates, a blue net, a green net, and an orange net. And I swap gates 1 and 2, the red gates, and now some of the nets are longer, some of the nets are shorter. It's exactly the same picture as before. Step 1, grab two gates, exchange them. Step 2, evaluate delta L, the change in half perimeter wire length. Do this incrementally, please, so that you do it efficiently. Step 3, the if conditional. If delta L equals the wire length got smaller, what do I do? If this is true, yes. Step 4, keep the swap. If this is false, no, undo the swap. Step 5, undo the swap. This is really where I need some new ideas, right? The idea that I should swap things to see if I can improve them, that's good. The idea that I should evaluate delta L, the change in the wire length, to evaluate the quality, that's good. The idea that I should ask the question, did it get worse or did it get better? That's good. The idea that if it got better, I should keep it, that's good. The idea that if it got worse, I must undo it and throw that away, that is what's got to go. We have to have something smarter here. And to have something smarter here, I need a really big idea. So, the big idea is something called, I'm going to call improvement with hill climbing, and we're going to sort of explain that. So, I've got grayed out here the previous parts of the algorithm that I said are good and worth keeping. 1, do the swap. 2, evaluate delta L, the wire length change. 3, if delta L got smaller. 4, yes, keep it. And what I'm going to do now is add some new sophistication. So what happens now is, amazingly enough, a thermometer appears in the right-hand side of the slide. Yes, a thermometer, like a little mercury thermometer, because everybody, I hope, recognizes that. And it says new. There's a hill climbing control parameter, which it is most easy to think of as the temperature, right? And so depending on how hot it is, that's how much hill climbing I'm going to allow in my algorithm. And now when we say, if delta L, the wire length that changes as a result of this swap, if it didn't get smaller, if it got bigger, I'm going to evaluate a new function, a mathematical function, P. P is a function of delta L, okay, the change in the wire length, and P is also a function of T, the temperature. And P, the result, is a probability, a number between 0 and 1, and it's actually going to be the probability that we should accept the swap. And what's going to happen is that I'm going to use that probability, and I'm going to generate a random number. Yes, a real random number, and that's why I'm showing you a picture of dice. I'm going to generate a number, and I'm going to randomly keep that swap with that probability. Now, this is all probably very confusing, so let's talk about this a little more algorithmically. So, again, I'm showing you the same picture of the swap, 2 black gates, 2 red gates, 3 nets, blue, orange, and green. I swap gate 1 and gate 2. The blue net looks longer, the orange net is the same length, the green net looks shorter. I calculate delta L, the change in the length, and it is longer. Okay? This swap made the wire length worse. And so I'm also showing you a picture of the thermometer. So what happens next? The delta L number and the thermometer temperature go into a mathematical function. That mathematical function is e to the minus delta L over t. That generates a number. And that number, because it's e to the minus something, is a number between 0 and 1. So I can treat it like a probability. So that number might come out to be something like 0.72. The way you think of that is, there is a 72% chance that I should keep this swap. 72% of the time I should keep this swap. 28% of the time, which is 1 minus 0.72, 28% of the time I should not keep this swap. I'm going to randomly keep this swap. How do I do that? I generate a random number, uniformly random, between 0 and 1. So, in most programming languages, if you call something, random with 2 parentheses, or, rand, right, with, 2 parentheses, you get a uniform random number between 0 and 1. I'm going to generate R, a uniform random number between 0 and 1, and I'm going to compare R to P. If R is less than P, then I keep the swap. If R is greater than P, I undo the swap. That's what it means to take this swap with probability P, because I'm going to get a different answer depending on how this random number turns out. And sometimes, for a swap with exactly this delta L at exactly this temperature, sometimes I won't take this swap. 28% of the time, in fact. And sometimes I will take this swap, 72% of the time. I know this sounds very strange, but this is how it works. We're going to talk about more of this in more detail. So, this is the macroscopic, the big picture. This is a new random improvement algorithm. It's almost the same as the old greedy one, but it's got 2 big changes. So the first is there's this hill climbing parameter T, which you can think of as a temperature. And the way this actually works is that you start the temperature hot, and you do many swaps. And then you cool the temperature a little bit, and you do many swaps. And then you cool the temperature some more, and you do many swaps. And so the temperature starts out very hot, and it gets cold as time progresses. And at any given temperature, we evaluate this magic function, e to the minus delta L over t, and if the swap makes the wire length worse, we accept it randomly with a probability. So here's how the algorithm goes at a very high level. At the start of my new random iterative improvement algorithm, I set the temperature to be very hot. And you know what happens when the temperature is very hot? E to the minus delta L over t. T is a really big number. E to the minus delta L over t is e to the minus something really close to 0. That's really close to 1. The probabilities are very high that I can take a big uphill move. And so one of the things that becomes possible is it becomes possible to go uphill a lot. You can take a move, a perturbation, an exchange, a swap, a change in the placement that really makes it worse because it's hot. But it doesn't stay hot forever. We cool the temperature slowly over all of the swaps. And when the temperature is cool, it is no longer possible to go uphill so big. It is only possible to go a moderate way uphill. But you can always take a downhill move. Right? And as the temperature gets colder and colder, you can't go uphill at all. So the big uphill moves, well, I can't really do those anymore. Their probability is just too low. And even the medium-sized uphill moves, the probability is too low, but I can always go downhill. So that's how you control the hill climbing. The hill climbing is controlled by a temperature parameter. You start the problem hot, and you cool it slowly over many, many swaps. When the temperature is hot, there is a high probability of being able to take a large uphill move. When the temperature is cold, there is a low probability. That's how you control the uphill exploration, so you just don't keep messing up the placement. And that's how you put this interesting form of randomness down deep inside the inner loop of this placement algorithm. So that's things at a very high level. And in the next lecture, we're going to sort of dive into this one in some algorithmic detail and explain why this really works.